So hi, everybody. I'm back again, now in a different office on a different day to conduct the second pre-sessional lecture for our upcoming course in Madrid. So after watching the first lecture, I thought it was worth pointing out what the purpose of these pre-sectional lectures are. It's really to provide background material that's going to become useful for when we discuss more applied models of text and other unstructured data when we are together. So the material that we're going through is perhaps a bit higher level or drier, more abstract. There are different, terms, some more, some less charitable for it. But the point is that when we meet, we'll be talking more about applications and papers and use cases with some of this background material already in place. So what is the subject for this second lecture? Well, in the first lecture, we discussed a simple statistical model of text and compared and contrasted likelihood-based inference with Bayesian inference in that simple model. And that sort of presented one framework for doing unstructured data modeling, which was within a statistical framework. Okay, so whether it was with or without prior distributions over model parameters, we were firmly within the realm of probability models. Now, the other tradition for modeling unstructured data, and probably certainly becoming, I would say, dominant approach to modeling unstructured data is neural network models. So we'll discuss much more when we're together, but ChatGPT and GPT-3 and Alpaca and all these new language models that you might have heard of are all based on neural networks. And of course, we're not going to detail the full complexity of the networks that underlie these models, but certainly when we're together, I want to discuss these models a little bit. And to do that, we need, I guess, a basic language, a basic jargon for talking about how neural networks are set up and a little bit about how they're estimated. Now, I should also say that the office that I'm sitting in has a kind of a weak Wi-Fi connection. So I am not with my iPad today. So I'm not going to be making notations on a whiteboard. I'm just going to be running through these slides. So it's going to be, I guess, a little bit less technical than it was in the first lectures. But this is really just to introduce some terms and some concepts about neural networks. All right, so let me click through. All right, so, when we talk about the growth of machine learning and the growth of AI over the last 5 or 10 years, a lot of this has really been driven by neural networks. So as I mentioned, that's certainly the case for the modern large language models, but it's also true for computer vision models. You may have seen, about 5 years ago, in fact, I'm now in my office at UCL. Just down the road, there's a company called DeepMind, which developed a algorithm for playing Go. And apparently Go is much more difficult than chess to solve for a computer. And a neural network model was able to beat, the Go champion about 5 years ago. Okay, there was a nice Netflix movie about that if you want to watch it. The point being that neural networks have been extremely influential in the way that sort of complex pattern recognition has been approached computationally, and that's led to these important breakthroughs. Now, while there's been this growth in interest in neural networks in the last 5 or 10 years, it's actually quite an old class of models. So I'm not sure when the first neural network was written down, but I wouldn't be surprised if it was in the 1950s or 1960s. And in fact, there was a moment of popularity in the early 1990s around neural networks. And then that popularity kind of died down a little bit, and other machine learning algorithms became more popular and more used. And the recent growth in neural networks that started about 5 or 10 years ago was driven by, I guess, a few interrelated factors. So the first, and I hope you see my little hand that I can use to kind of direct us through the slides, is if you have these big complex models, you sort of need large data sets to train their millions of parameters. So increasingly, as we move to the digital age, we have lots of data recorded on digital platforms, which provided these large data sets for training neural networks, right? So we were no longer training on, 10,000 data points. We start training on 10 million data points. There's also been hardware advances that have led to the ability to estimate large models efficiently from a computational perspective. So that includes GPUs, which are graphical processing units. More recently, something called TPUs or tensor processing units. So those are basically computer chips that let you massively parallelize low latency operations, which neural network computations are filled with. And we've also seen the development of cloud infrastructure, which lets us run these specialized hardware on other people's infrastructures rather than our own laptops. So we don't actually have to invest in these chips. We can let other people invest in them, like Google or Amazon Web Services, and then achieve economies of scale through using those intensively. There have also been software advances. So as we'll see in our course, you can now interface with neural networks with fairly high-level frameworks. So you don't have to build these things from scratch. You can interact with them via high-level APIs, which makes them much more user-friendly. And there's also been some algorithmic advances on, in particular, how to compute gradients efficiently, which we'll discuss a little bit later in the slides. So basically, these sort of four complementary features of data, hardware, algorithms, and software have all combined to create this explosion in use cases and power of neural networks in the last 10 years. So what are we going to do in this lecture? I basically just want to describe the simplest neural network that I can, and that is something called a feed-forward neural network. Now, these are not directly applicable to text, but at least they provide a sort of initial set of ideas, which we can then enrich when we come to model not just text, I should say, but other unstructured data. All right, so let's talk about the basic architecture of a neural network. All right, so let's say that we have some observations, okay, and those observations are going to be indexed by I. So those may be, individual documents in a textual database, or individual images in an image file, or in standard data, I could index a person, right? And then each observation has a set of observable covariates, and let's say that there are capital J observed covariates. So in the last lecture, the observed covariates, you could think of them as term counts if we were in the world of text data. If you're in the world of image data, you could think of X as pixel counts, for example. And if we're in the world of, say, traditional data, XI could encode somebody's age, gender, and income. Okay, so these are just meant to be standard covariates. All right, so the first step in building a neural network is to consider a linear combination of these covariates. So this, in fact, looks very much like a linear regression. We have our covariates. Each one is assigned a parameter that lies in the reals typically. So this theta j is the parameter associated with the jth covariate. And here I'm just taking the linear combination across all these covariates and adding a constant term. Okay, so this is literally kind of what we do when we specify a OLS model. Now, in neural network jargon, these parameters have some terminology attached to them. And I have to admit, I'm not entirely sure why this terminology developed, but I'll just share it with you, given that it exists. So these parameters that represent I guess we would think of them as the quote unquote coefficients on the covariates, are sometimes called weights in this neural network literature. And the theta 0 is called a bias. All right, so rather than having a constant and coefficients, we have a bias and we have weights. Okay, so the first thing to say is that neural network models have a kind of linearity about them. All right, so we don't have, weird nonlinear terms that we are using directly in forming this object here. Okay. Now, where the nonlinearity comes in is we're going to take the linear combination of covariates and pass them through a nonlinear function. All right, so we're going to take this zi, which is a scalar. Okay, so once I linearly combine my j covariates and add a constant, that's just going to be itself a constant. So I'm going to take that constant zi and push it through what's called an activation function. And this activation function can take different forms, as I'll show you on the next slide. But it's going to give me some new output. But this activation function is the source of nonlinearity in neural network models. All right, so what are some possibilities for our activation functions? Now, if I had my whiteboard with me, I would maybe manually write these functional shapes, but you'll see in the next slides I've actually graphed them. So I guess the most classical, if you were to pick up, for example, papers on neural networks in the 1990s, the most popular form of activation function was the sigmoid function. Okay, so if you take this linear combination of covariates and pass it through this sigmoid function, in econometrics, we would call that a logistic regression, right? So indeed, this is nothing more, if we were to stop at this point, than specifying a generalized linear model with a logistic link. Okay. You could take the limit of this sigmoid function to create a step function. There's something called a hyperbolic tangent, which I'll show you in the next slides. And then you could also just have the identity function, which is a just returning the zi itself. Okay, so that would be linear regression. Now, in the last 5 or 10 years, there have been other activation functions proposed. So one is called the rectified linear unit, all right, which my understanding is that this was developed to avoid something called the vanishing gradient problem. So if you think about the logistic regression, as you get far, far out in the tails of the logistic regression, the gradient of this function starts to collapse to 0, okay, which can create problems for numeric optimization algorithms. This rectified linear unit is not going to have that property. So as zi gets big and big and big, the gradient is going to stay bound away from 0. There's yet another activation function that's the soft plus, but let me not belabor this zoo of activation functions. The point is that we have some nonlinearities induced by some activation function, and these are the most popular choices. All right, so here we go with the plots of some of these. So this is a simple sigmoid function, all right, that's traced out here in red. And then the hyperbolic tangent, you can see has a qualitatively similar shape to the sigmoid, and it is traced out in blue. The rectified linear unit is traced out in red here. So you see what I was saying, that the gradient of both the hyperbolic tangent and the sigmoid function is going to be limiting to 0 as z gets big. And that is not going to happen with these two rectified linear unit and soft plus activation functions. All right, now the point is that when I go estimate my neural network, I'm going to be estimating the parameters of the z input into these activation functions. All right, so notice the subtlety here. So these graphs that I've just shown are plotted in terms of the z's, all right? So now I'm looking at a plot in terms of the x's, where I am varying the weight that's multiplying these x's, all right? So this is a case where we have a single covariate x, and we're ranging between -10 and 10, and I'm plotting out the sigmoid function that's formed by multiplying x by different values of a weight. All right, so the weight of 1 is represented by the blue function, and that should look exactly like this red function here, okay? But the point is, if I change the weight on the x, the shape of the sigmoid function in x is going to look different, all right? So the smaller and smaller the weight, the flatter and flatter this function gets. I can also transpose the function, right? So if I use a weight of -1, I'm gonna rotate it basically about the y-axis. And so when I go to estimate a neural network, I'm sort of making these choices about how flat or flipped or steep these underlying activation functions are going to be. If I vary the bias while keeping the weight constant, so just to be clear, in all of these plots here, I was keeping the bias fixed at 0. In these plots, I'm keeping the weight fixed at 1, but varying the bias. So as I move the bias up, I'm going to be shifting this sigmoid function around. And in the end, I'm going to be combining the bias with the weights to form different shapes for my activation functions. Okay. All right, so why is this called a neural network? Well, the idea of a neural network comes from the structure of neurons in our brain. All right, so I'm not a biologist, so I don't want to, read too deeply into any of this. But the idea is I have a set of inputs. Okay, so those are my x's corresponding to each one of my observations. So you could think of that as signals entering a neuron, which are the cells that make up our brain, and then they get kind of passed through our brain cells and creates outputs. Okay, so apparently this is how our brain works. It takes electrical signals into one part of the neuron, passes it down, and outputs them into another through some transformation. That's why they're called neural networks. I haven't met anyone who thinks this is a good analogy for what they actually do. Okay, so I don't think that we should think of these neural networks as a biological model. Okay, it's just, if you're curious about where the terminology came from, it comes from sort of some loose understanding of how neurons in our brain are structured. Okay, but enough with the kind of sexy biological analogy. Let's turn to a more formal definition of what a neural network is. All right, so that individual element that we described 3 slides ago, so this, sorry, I guess it's 6 slides ago. This thing is referred to as an individual neuron. All right, so this process of taking a linear combination of our input data X and passing it through an activation function represents the operation of a neuron. A neural network takes different neurons together and combines them. All right, so now, rather than there just being one operation of taking in a vector of covariates, linearly combining them and passing them through an activation function, we're now going to do that capital K times, right? So this formula here is exactly the same as what we had for our case above, except we've now added a K, right? So the idea is we now have K distinct linear combinations of our covariates, and each one of those linear combinations has its own index K. Okay, so every observation I is passed through all of the capital K different neurons. And so in the end, my data becomes, capital N by K. Okay. Then in my final layer of my neural network, I'm going to take those K different linear combinations of data passed through an activation function and again linearly combine them. All right, so each one of my K activations is going to again have a parameter, okay, theta K, and a bias, theta 0. And that in the end is going to be my final function for describing how I'm mapping the input data X into some output data f of X. Okay, so the only thing that we've done here is defined in a very particular way a nonlinear function. Okay, so every observation has this set of j covariates, and this simply defines a nonlinear mapping of those j covariates into some output. Okay, this is called a single layer neural network. Okay? So in some sense, it's highly linear because we have these capital K linear combinations, and the final output layer is also a linear combination. So the nonlinearities, as I said, are induced by these nonlinearities in the activation functions. So if I had a big whiteboard, we could start to draw out what might be happening here, but maybe I can just verbally describe it. So each one of these capital K neurons in this single layer neural network is going to be representing a different sigmoid. Okay, if we consider the activation function to be a sigmoid. So I'm basically going to be placing capital K different sigmoid functions at different places in the covariate space, and those individual sigmoid functions can be flipped, stretched, translated in different ways. And then in the end, I'm going to be adding them together to form a final function. So you can see how these nonlinearities can start to develop when we have different parts of the covariate space being represented by these different nonlinear sigmoids. Okay? All right, so you may wonder what's the big hype around forming this particular nonlinear mapping of covariates into outputs, right? Because there are many nonlinear mappings of covariates into outputs. I could define, for example, a polynomial, right? Like a 10th order polynomial. Why not? I could do something like write down decision tree. That's another nonlinear mapping of inputs into outputs, right? So what's special about this particular mapping of inputs into outputs? Well, there has been a little bit of theory work on this. All right, so interestingly, even though neural networks are associated with the computer science literature, Hal White and other econometricians came up with a universal approximation theorem about neural networks, I guess about 30 or 40 years ago. So I don't want to get into the technical details, but basically the idea was a large class of functions can be approximated with an arbitrary amount of accuracy with a neural network. Okay? So that doesn't say that other nonlinear functions might not also do that, okay? But it says neural networks are able to do that. Now, you might have to, create many individual neurons, so capital K might have to be big. But eventually, if you have enough neurons, you're going to be able to approximate to an arbitrary degree of accuracy a broad class of nonlinear functions. And by the way, if you go to the end of these lecture slides, you'll see the reference. In fact, I think you may be able to click the slides. There you go. Okay, so there's a journal called Neural Networks, and the reference is there. All right. The second result is also kind of interesting. So again, maybe I wrote this down in a little bit too much technical detail, but this says something I think more interesting, which is that a one-layer neural network can achieve some approximation of a nonlinear function more efficiently than traditional series approximations. Okay, so for those of you who do, nonlinear function approximation in econometrics, a very traditional way of doing this is through some basis function expansion, right? Or other series-like approximations. So basically, at a high level, this theorem says that neural networks are more efficient at approximating, in particular, high-dimensional functions than basis function expansions or other series expansions. Okay? And I guess a rough intuition for that result is that when you let's think about a polynomial function, for example. So let's say we wanted to approximate a nonlinear function with like a fifth order polynomial. Well, there's a kind of, if you change any of the estimates, any of the coefficient estimates in your fifth degree polynomial, that's going to have implications for the global shape of the function, right? So if you start manipulating the coefficient on the quadratic term, that's going to change the shape of the function across the whole input space. But when you think about a structure of a neural network, you can actually, if one part of the input space has a strange shape, like, you know, locally it's very steep, for example, you don't have to change the global structure of the underlying function. You can just take a particular sigmoid, line the sigmoid up in the particular part of the input space where that steepness needs to be captured, pick a weight that makes the sigmoid very steep, and the rest of the function approximation is relatively unaffected. Okay, so you're doing basically a series of local approximations through these sigmoids, which you then add together into the full approximation. Whereas the fifth order polynomial has parameters on each one of the polynomial terms that basically define global behavior, not just local behavior. So that's a very rough intuition. You can, you know, if you want a more formal discussion of all of these issues, I invite you to, you know, to take the reference and read the paper. Okay, so in principle, those two results are good news, right? So I can approximate complicated functions well, and I can do so efficiently. Okay, in particular when those functions become high dimensional. Now, those are true in theory. In practice, one-layer neural networks are not estimated very often. Okay, in particular, not in the context of text and other unstructured data. So instead, what tends to get estimated are multi-level models. All right, so we don't just create linear combinations of inputs and pass them through activation functions and linearly combine their outputs. That's a one-layer neural network. We do those operations again and again and again and again and again. All right, and that is sometimes called deep learning. Okay, so a deep neural network is one with many layers stacked one on top of the other. Okay, so this slide defines what a multi-level neural network looks like. So our basic operations that we saw in the previous slide are basically being just replicated here again and again and again. So I'm going to start with my input layer, which is going to linearly combine my covariates and produce these outputs. Okay, and I could do that capital K times, for example. Then, well, I guess I'm saying capital K1 to indicate that those operations are all being done on these input data. Then I'm going to linearly combine all of the capital K1 neurons from the input layer together to create new outputs. And I can do that capital K2 times. And then my hidden layer 2 is gonna linearly combine those inputs, and so on and so on and so on and so on, until I get to my output layer, where finally I'm going to stop. Okay, so this is just repeating the same operations that we discussed before multiple times. Okay? So this is called a feed-forward neural network. And if you want a visual representation of what's going on, we take our input space, we pass it through an initial layer of neurons, which then feed into a subsequent layer of neurons, which then feed into some outputs. Okay. So for some reason, the computer science literature uses these graphical representations of neural networks quite a lot. I find them in some cases helpful, in some cases not. I always feel more comfortable when I know the actual mathematical definition of a neural network. So that's why I write this down, but some people like these graphs as well. All right, so why, and here we are in a world with less theory, okay? So I can quote these theorems from the literature on why these one-layer neural networks might be a good idea to use, but why in practice do people use multiple layers? I mean, there probably by now do exist theorems about this. I don't study the neural network theory literature very deeply. But from a more engineering perspective, there are certainly cases, a case to be made for why multiple layers might be useful. So basically, the rough idea is if you take, let's say hundreds and hundreds of covariates, like let's think about text data where I might have 10,000 terms. Building multiple layers allows sort of complex correlations to be resolved step by step rather than all together. Okay. So if I want to build, complex representations of language, it might be useful to, for example, first understand what verbs, subjects, objects, and prepositions are. All right. And then after I've understood what those are, I could start combining, verbs and subjects together. So I could start saying things like Stephen runs. And then I might start combining other things together, right? Like Stephen runs to the store, and sort of progressively build up more and more complex structures from simpler base structures, rather than doing everything at once, taking a set of terms and having to understand everything in one layer. All right, so more or less, what you're thinking about as you pass through the different levels of a neural network is that different structures are emerging at each level. And doing that in sequence can be an easier problem when you have highly dependent data than just in one shot, okay? So I think that becomes particularly clear for image data. So when we talk about convolutional neural networks in our class, we can come back to this idea of sort of complex structure emerging gradually through the different layers of a neural network. Okay. All right, so for that reason, it's typical to have fewer units as we move along a network. So if you look at this graph, for example, you see that our data is sort of being compressed more and more as we move up the network. All right, so we start with high dimensional inputs. The first layer does a little bit of dimensionality reduction. The second layer does more dimensionality reduction. The output layer does even more dimensionality reduction. Okay. So you can output real numbers as the output, right? So that's map a high dimensional input into the reals. You can also, if you're doing a classification problem, map the final output through a this is in the machine learning literature sometimes called a softmax function. We might call it the multivariate logistic function. So basically creating class probabilities, right? So trying to use input data to predict whether input is spam or not spam, or is it an apple, an orange, or a plum if you're putting in image data. So basically doing a discrete number of class prediction probabilities. All right, so how do you estimate these models? So I should be clear, by the way, that these structures are not explicitly set up as statistical models. So when I say estimation here, I'm not really talking about statistical inference, right? Because we typically don't think about these as parameters of some underlying likelihood model. All right, this is just a way of parameterizing a nonlinear function. All right, so the typical way that these neural network parameters are estimated or learned, again, I'm using those terms interchangeably, is to define a loss function, first of all. All right, so the output of my neural network is ultimately this function. All right, so I have my input data xi. I have my parameters theta. And those parameters are going to represent all of the aspects of my neural network, right? So this is going to be all the weights and the biases from all of the neurons and all of the layers. So this is going to, be hundreds, millions, billions, depending on the size of the neural network. But ultimately, every observation I is going to have a, some output associated with the neural network, which we're going to call f of xi given theta. There's then going to be some, observed outcome for that observation I, which we can call yi. And my loss function is just going to be some average loss over all observations, where the loss depends on the true value of I, or this observed value yi, and the output of the neural network. So there are many loss functions in the literature. I think the two most commonly used, at least for feed-forward neural networks, is if you have a continuous output yi, the simple squared error, right? So I guess that basically implies that the loss function is going to be the mean squared error across all observations. If you have a categorical yi, this is sometimes called the cross entropy, but so here yi is going to be, so this loss function is going to be low when the predicted probabilities for observation I correspond to their class label. Okay. All right. So how do I, given a loss function, how do I actually start estimating these thetas? So almost invariably, neural networks are trained using some variant of a gradient descent algorithm. So I'm first going to randomly initialize some parameters, right? And then I'm going to update those parameters based on the gradient of the loss at the current value of those parameters, right? So I'm just going to iteratively update my parameter estimates in the direction of the gradient of the loss function at the previous values. And the amount that I move in the direction of the gradient is going to depend on something called the learning rate. All right, so that's typically set to a small number, so that I'm not going to adjust my parameters too much at any given pass through this gradient descent algorithm. But I'm going to do a controlled sequence of small steps in the direction of maximum descent, which is given by the gradient. Okay. All right, so it turns out that computing the gradient in large-scale models is expensive. So think about, training GPT-3. I don't know how many input documents would have been used for it, but I'm sure that we're talking about billions and billions of documents. And computing the gradient of the loss function involves computing the loss at every single observation of the input data, okay? And that is expensive. So instead of full gradient descent, a popular alternative, and this again is for speed reasons, is something called stochastic gradient descent. All right, so stochastic gradient descent basically creates an unbiased estimate of the gradient by only computing it on a randomly drawn subset of observations, okay? So we're basically going to take a random draw of data and compute the gradient of the loss function with respect to that randomly drawn subsample. That's going to be a lot faster, okay? There is some theory, by the way, about why stochastic gradient descent is a well-behaved optimization routine, but I won't go into that now. But introduce yet more jargon from the literature. The data that goes into one of these stochastic gradient computations is sometimes called a batch of data. Okay, where capital NB, we can think of it as the batch size. Okay, so let's say you have a batch size of 50. That would mean that at every pass through your gradient descent algorithm, you would be computing the gradient with respect to 50 data points. Okay, that would be a batch size of 50. An epoch or epoch, I've seen this pronounced different ways, is a single pass through all of the training data. All right, so you go, you take 50 data points, and then maybe another 50 data points, and then another 50 data points. And whenever you've passed through all of the training data in one cycle, you've completed one epoch of training. Okay, so when you go parameterize, or when you go optimize a neural network in Python, as we'll do in our tutorials, these are all going to be parameter choices, right? The learning rate, the batch size, the number of epochs you want to run, and so on. Okay. All right, so I guess the final thing that might be worth mentioning is that in addition to stochastic gradient descent, there are other tricks for speeding up these gradient computations. So one popular approach to this is something called backpropagation, all right, which is essentially a way of efficiently implementing the chain rule. So if you go back to the structure of a feed-forward neural network and think, for example, if I wanted to compute the gradient of this feed-forward neural network with respect to one of the weights and one of the hidden layers, well, I'm essentially going to be using the chain rule, right? Because that weight is going to show up in the output layer. Then I'm going to take the derivative of that with respect to the weight, and then that's going to be fed down throughout the network. Okay, and backpropagation is a way of keeping track of all of the derivatives taken as I pass from the output layer through all the hidden layers. And yeah, it basically tells the computer how to do the chain rule efficiently. And combining that with GPUs and TPUs is really the secret sauce for estimating modern neural networks. So stochastic gradient descent, plus backpropagation, plus deploying all of this on GPUs and TPUs is how all of these big complex neural networks are estimated in practice. Okay. So I guess the final thing to mention is, as in other high dimensional models, regularization can be important, or is important typically. So there's different ways of approaching this in a neural network. So sometimes a ridge or a lasso penalty is added to the loss function, right? So we don't just use the raw loss function. We would, for example, add the some weighted sum of squares of the underlying thetas, or the weighted absolute values of them if we wanted to do a lasso loss. A second idea is dropout. All right, so dropout implies that at every pass through our stochastic gradient descent model, we're going to randomly essentially drop nodes. All right, so we're going to zero out some of the parameters to make sure that no one node is overly influential in any particular prediction. Okay, so it's like randomly deleting parts of the model to make sure that that no one part of the model is driving everything. And then my understanding is that there's just a large, I'm certainly not an expert in this area, but there's just a large number of parameters to tune in a neural network, right? So how many nodes do I put in any given layer? How many layers do I have? What's my learning rate? Do I use a rectified linear unit or a sigmoid or whatever, right? There's all of these things that go on in the background. And typically there's very little theory to guidance choices. So there's a lot of just playing around with which models work and which models don't work, where the definition of work is always, does it perform well in some held out test data? Okay. So we can talk a little bit more about this when we're in person, but I just wanted to, set the scene a little bit, as I said, for what we're going to end up talking more about in a couple of weeks. All right, so this, I guess is a concluding slide. So I would say that, as a nonlinear approximation algorithm for standard data in a standard regression setting, I'm not sure that I would use neural networks. Okay, so I think for for sort of regular tabular data. If you want to use a nonlinear model, I think random forests and gradient boosted trees are typically the go-to models, not just because they are more simple computationally, but I think there's also some theory now even about how to do inference in them. Neural networks are they're bigger, they have many more parameters, they are often need to be, engineered very carefully, as I said. So, for standard econometrics, I'm not sure that neural networks are ultimately that useful, but they're certainly useful for unstructured data analysis. All right. So the reason that I'm introducing them is because they're at the heart of a lot of these modern advances. And so it's good to have at least a little bit of an understanding of what's going on. All right. So I'm going to stop recording. This is our final pre-sessional lecture. I hope you find them useful. Again, if you find them a bit dry, don't worry. We'll make all this come to life in a little bit. And yes, I will sign off now and see you on, I guess, a week from Monday. Bye-bye.